Hi everyone, my name is Shamik and I'm a product manager here at MongoDB. Thanks for tuning into my session. Imagine this. Imagine you're a developer who's building out their dream of a next generation e-commerce marketplace. Things have been going great for your app. And tomorrow it's Black Friday. Everyone's using your app to get their hands on a PS5. Here are two scenarios that could go down for your customers tomorrow on Black Friday. Alice, one of your customers, used your app to finally secure her PS5. She was on the PS5 order page, she hit purchase, she got a success message, and then she finally closed her laptop. But she waited a couple of hours to track her order. And when she finally went to check, she realized that her order never actually went through. Another customer, Charlie, also placed his order for the PS5. He also got a success indicator that his order is on its way. But unlike Alice, he went to check his order history immediately. And his dashboard didn't show his order either. His reaction to this was to place his order again. 10 minutes later, when he went to check on his order dashboard one more time, he realized that his first order actually did go through. And so he ended up unintentionally making two purchases. In both of these scenarios, there weren't any pesky bugs, there weren't any app server hiccups, and your users weren't doing anything wrong. The problem came from the decisions and actions taken by your database based on the durability, consistency, and isolation settings your database had at that time. Durability, latency, consistency, isolation. Our database has so many possible performance-related settings, and each one comes with a trade-off. But here's the thing. You may already be making these trade-offs and not even be aware of them. And that's okay, because in this session, we'll learn all about them. If those words were a bit foreign to you, if you're new to MongoDB, or just simply looking to sharpen your MongoDB knowledge, you've come to the right session. We'll start off by learning about MongoDB's replica sets so that we can get a baseline understanding of how everything works. We'll discuss what the different settings are for reads and for writes, and what they are by default, the different trade-offs they come with, and then finally, we'll take this understanding so that we can understand how to pick the right combination for our own applications. Great, let's get started. To understand why these trade-offs have to even exist in the first place, let's take a look at a typical MongoDB production deployment, a replica set. A replica set is several MongoDB instances that maintain copies of your application's data. One node in the set is responsible for taking in writes, the primary node, while the other nodes are responsible for maintaining copies of the primary's data, the secondary nodes. The secondary nodes are also responsible for electing a new primary should the current primary fail. These secondary nodes asynchronously apply writes to its copies of the data as they happen on the primary. And all nodes in the replica set communicate via heartbeats so that everyone is aware of what the current state of the replica set is. MongoDB runs on replica sets for a couple of reasons. Multiple data-bearing nodes maintaining copies of the same data guarantees high availability, that your MongoDB cluster will operate continuously without failure. In the real world, we know that a machine has some chance of going down. It could be due to network outages, physical failures, or more. But because there are multiple nodes that maintain the same data, if one of them goes down, the other replicas can resume responsibility and keep the cluster up and running. Let's go over what that looks like. Let's say we have a 3-node cluster that's taking in writes and reads from our application just fine, and something happens to the primary. When the primary can't be reached, the secondary is marked that primary as inaccessible and start an election to determine the new primary. The secondary is no to do this since the heartbeats that they maintain to the primary aren't being satisfied. A cluster does not accept writes while the primary is down, so the secondaries work super hard to make sure that the system can go back to accepting writes as soon as possible. The secondaries determine that next primary through MongoDB's special election algorithm. And voila! After the secondaries elect a new primary, the replica set can go back to accepting writes, and everything is back to normal again. MongoDB drivers will automatically detect which node is the new primary after the election, and they will retry writes on the new primary. The new primary is elected just within seconds of the former primary going down. Because of the high availability afforded by MongoDB's replica sets, we're able to reduce our write delay to just seconds. This would not be possible if we deployed our cluster with just a single node. There's one last thing to keep in mind with elections. Let's say right before the old primary crashed, it had accepted a write operation, but that write operation did not replicate to the other nodes just yet. If the old primary accepted a write that never replicated, then the newly elected primary will not have that write. And so when the former primary rejoins the replica set as a secondary, it has to revert or roll back the previously accepted write operations. MongoDB does this to keep the data consistent on all replica set members. Now that we understand replica sets and how they guarantee high availability, we can dive into checking out the different options you have with how replica sets handle writes and the trade-offs that they come with. As I mentioned earlier, an application writes data to one node, the primary node. And when that write operation comes in, two important things must happen. First, MongoDB executes the write. Second, MongoDB sends an acknowledgement back to the application that the write operation has succeeded. When is it considered that the write operation has succeeded? That's up to you. You can choose how many nodes have to acknowledge a write. In other words, you can control how durable a write must be for it to be considered successful. We do this via a setting called write concern. It answers the question, how many nodes have to successfully write the data for it to be acknowledged? The more nodes that execute a write, the more durable that write becomes. And durability is the guarantee that written data has been saved and that it will survive node failures. With write concern, you can set this acknowledgement to be from no nodes to all nodes. Let's go over what each option gets us. If you set write concern to 1, this means that only one node needs to execute that write, the primary node. The secondary nodes will still apply those writes to their copies of the data, but the write acknowledgement won't wait for any of those actions to complete before returning a success. As long as the primary does its job, the application will get a success message. You can also choose write concern majority, which means that more than half, or a strict majority, of the nodes in a replica set have to execute that write. At this point, our write is considered durable. Any combination of these nodes can satisfy the write concern majority as long as it's a minimum of the majority number of nodes. It can be this combination or this combination, any combination as long as it's a majority. And theoretically, you can choose any number. But be careful. Choosing a write concern of 0 means that your application will not wait for any guarantee from the cluster to send a success response. For that reason, we don't recommend a write concern of 0. And theoretically again, we could set our write concern to be all nodes in the replica set. Sure, we get the highest durability possible, but here we compromise in availability. If just a single node in our replica set goes down, our cluster will not be able to acknowledge writes. And again, what's so great about durability? Well, it's the guarantee of not losing data. That by making sure a write is acknowledged to a majority of our nodes, we guarantee that it won't be lost during a failover. It may seem that going with greater durability is a no-brainer, but we realize that opting for greater durability comes with trade-offs. This greater durability comes with the trade-off of latency. The more nodes needed for acknowledgement, the longer your application has to wait. So, as you increase the number of nodes needed for acknowledgement by choosing something like let's say W majority, there will be an increase in latency for an individual operation to send its acknowledgement as compared to, let's say, W1. Remember Alice, the customer from our first scenario at the start of this session? She placed an order for her PS5, but it never went through. Well, the reason for that was because your application used the default write concern of W1. The write came into the primary and it was acknowledged, but before it was replicated to the other secondaries, it crashed. There was an automatic failover and that write was rolled back. So Alice's order was never saved. And now, something important to know. Starting in MongoDB 5.0, the default write concern will be majority. Previously, this value used to be W1. We made this change because we want to provide our customers a safer, more durable experience with MongoDB out of the box. And well, what does this mean for you? If you already explicitly set your write concern, this change won't impact you. However, if you never set the write concern explicitly, when you upgrade to 5.0, your write concern will become majority. And if you prefer the former default of write concern 1, you can set it back to that. And now, on to read operations. When it comes to the data that a read operation returns, there are a couple things that we care about and can control. First is durability. Remember how we talked about data durability with write operations? Well, that concept transfers over to the data that we read from read operations as well. In this context, it's about the guarantee that the data we read can be considered saved safely. Second is consistency. This is the property that says our read operations return data that reflect the results of the writes that came before them. Third, availability. An operation is considered available if the cluster is able to satisfy the requirements for the first two properties. If this is the case, the read operation will get back a success response. Otherwise, it will get an error. And fourth, latency. We want all of these great properties, but of course, we also want our reads to be as performant as possible. The knobs that we have to influence these desirable properties are called read concern and read preference. These settings sound very similar, but in reality, they're very different. Let's start off with read concern. Read concern is a setting that lets us control how durable and consistent the data that a read operation returns must be. The three options with read concern we'll review are local read concern, majority, and linearizable. As always, let's learn these options by going through an example. Let's say an application is sending a read to a replica set. A read operation only needs one node to read from. So let's peek into the documents that's currently in the node we're reading from. Documents are either matched or not matched in our read. Here, the gray dots represent documents that aren't matched. Since we won't be returning them, we don't have to be worrying about them in this example. When we're left with our matching documents, we can see that a matched document can either be durably committed or not durably committed. As a reminder, data is durably committed if a majority of replica set members have that version of the data. With our first read concern, we will just be returning any matched document on the node. This is the default read concern. So, all the documents that match our read are returned. Local does not guarantee that the data that we're getting back has been majority committed. It just returns what it has. Because of this, the durability guarantee from local isn't that great. It's possible that our application gets data that will be rolled back if a node failure happens. The next option is read concern majority. With this setting, an operation only retrieves data that was committed to a majority of replica set members. Each node keeps a record of what durably committed data it has at a certain point of time. So in this case, our read only gets the top 2 rows, which are only durably committed matched documents. Each replica set member has its own understanding of this. And because replication lag is possible, this understanding may not be the same across all nodes. This snapshot only reflects the results of writes that are majority committed. It does not reflect the most recent dataset on the current node. And because of this, read concern majority does not guarantee that the data we are receiving is up to date, which we can see because we're not getting back the last 4 rows of data. Those last 4 rows match our read query, they're on this node, but because they aren't durably committed, we're not getting them back. And so we can consider our results not up to date. Last, we have read concern linearizable. Here, we only return both durable data and data that is up to date. Read concern linearizable enables this since any operation with this read concern will block until the most recent last write has been majority committed. Since we wait for the most recent write to become committed, we ensure that the data is up to date. And since we wait for this most recent write to be majority committed, we can also guarantee that the data is durable. So, the data in our example gets back data that is both durable and up to date. However, waiting for this most recent write to become majority committed may mean that our operation waits for a long time. The trade-off we make here for durability and recency is latency. With linearizable, our operations may wait a while. Great, so that's how we control the durability and consistency of the data we get back. And now on to the last setting, read preference. Up until now, we've talked about the different rules that we can apply for what data to retrieve from the node we're receiving from, but the question then comes up. To which node should we be directing these reads to? Read preference answers exactly that. It lets us specify which node in a replica set the MongoDB driver will route its read operations. Unlike writes, you can target read operations to be any node in a replica set. Data-bearing nodes in a replica set can be either a primary or secondary. So let's talk about what happens when you read from each one. First, reading from primaries. A read preference of primary always routes reads to primaries. This is the default option, meaning that unless you change the setting, by default, your reads will go to the primary. Reading from primaries have the benefit of always reading your own writes, since you're always reading from the nodes that always has the most recently written data. But this comes at the cost of availability. If the primary is unavailable for whatever reason, your app can't service reads. And so how do you ensure that your reads are as up to date as possible while minimizing unavailability? Use read preference primary preferred. Here, our application will read from the primary under normal circumstances, except when the primary is unavailable. In this situation, we will allow reads from secondaries. If a read has been sent to the primary that is unavailable, and it has the read preference of primary preferred, MongoDB will reroute that operation to a secondary and return the data that the secondary has. So, with read preference primary preferred, we're getting our read your own writes guarantee except during elections. But at least during elections, our reads are considered available. A read preference of secondary always routes reads to a secondary node. But because of possible replication lag, these reads don't guarantee that you read your own writes. So, we may be getting back stale data. But there are a couple of reasons on why you may actually want to direct reads to secondaries. You may have some sort of resource-heavy operation, like let's say a backup or an analytical query, and you don't want that operation to interfere with the primary's workload. And so for those operations, it might not be so important that the data it's doing some analysis on is up to date, but what's important is that you're able to isolate that read operation from the primary, since the primary will be handling writes. And so use read preference secondary for achieving workload isolation. The other reason why you'd want to read from a secondary is to allow low latency reads. Our last read concern option, read preference nearest, is perfect for that. Read preference nearest says that an application is okay to read from either a primary or a secondary. It just needs to read from the nearest node. And so here, nearest means the lowest ping time between an application instance and each member of the replica set. This option is great if low latency reads are critical for your app, and you're okay with the trade-offs that come with reading from a secondary. And so now, going back to our second customer from earlier, Charlie. Charlie ended up accidentally ordering two PS5s because when he went to go check on his order, it did not show up the first time. This happened because behind the scenes, your application was reading from a secondary. The first time Charlie opened his dashboard, we were returning a stale read. The simplest way to make sure that this couldn't happen is if you read from the primary, since the data that a primary would be returning would be up to date. All right, you've learned a ton about replica sets, read concerns, write concerns, and read preferences, so please pat yourself on the back. At this point, we know well that every decision we make with these settings comes with benefits and sacrifices. And so finally, let's talk through how we can fit all these options together for your own application. The most important thing when choosing which trade-off to make is keeping your end users in mind. When you stick with the default or make a change, ask yourself, how will this change impact them? When opting for durability with majority writes, you accept a slight increase in latency. When opting for consistency by reading from a primary, you sacrifice in availability during elections. When opting for latency by choosing nearest reads, you sacrifice in consistency by accepting to read from a secondary, whose data may be stale. When opting for durability by choosing majority reads, you sacrifice in recency by not returning non-durable data, yet recent data that's already on a node. And the great thing about these settings in MongoDB is that you have so much control over how these knobs get applied to your application. You can set read and write concern on a per cluster, per application client, per database, per collection, or even at the individual operation level. And read preference can be set at the client and operation level. So this means that some of your operations may have a write concern of majority, while the others have a write concern of 1. Some of your reads may be majority reads, while the others are local reads. Some of the reads might go to primaries, some of them may go to secondaries. You get exact control. The last thing that I want to say, go out there and learn about your users, about the different expectations that they have, about what habits and reactions they have. Translate these expectations into the different settings that we talked about today. The most important thing, keep learning about your customers and keep iterating on these settings. That way, you not only know what the different trade-offs look like for your app, but you can be confident that you're choosing the most appropriate setting. MongoDB will have your back when you need to make the right trade-off. Thank you so much for tuning into my talk. I hope you learned a lot, and I hope you enjoy the rest of MongoDB Live 2021. Thank you.